Hello. To understand intraocular pressure mechanics, it requires an accurate mathematical description of the actors involved in fluid coming into and leaving the eye. Aqueous dynamics in the literature and in teaching begins with a basis in the Goldmann equation. This has bothered me for almost 30 years since it was first taught to me and makes it look as if this were a simple linear equation. It is not. The outflow facility C is not an independent variable. It is actually dependent upon intraocular pressure as noted by its units, microliters per minute per millimeter of mercury. With this equation, we cannot calculate intraocular pressure. Furthermore, we cannot provide a quantitative understanding of how the factors affect intraocular pressure. Using the fluid-filled tank analogy, this simplified description of fluid in divided by fluid out plus episcleral venous pressure equals intraocular pressure is incorrect, but it is pervasive in the clinic, in the lecture hall, and in the literature. Even on its face, if fluid in doesn't equal fluid out, then the pressure is forever increasing or decreasing. The problem is the outflow facility C is dependent upon intraocular pressure. So now in this equation, you have intraocular pressure on both sides of this equation. But not only is it dependent upon intraocular pressure, but the rate of change in intraocular pressure. I assumed that the description of this equation would evolve over the last 30 years to what I understood was actually a differential equation as noted here. This equation describes the fluid out as a function, not a variable. With this, we are able to calculate intraocular pressure, and it provides a quantitative understanding of how the factors affect intraocular pressure. The correct interpretation of fluid out is as a flow restrictive function altered by a change in intraocular pressure. This altered equation can now fully describe the fluid mechanics of all manner of both natural and interventional intraocular pressure behaviors, such as trabecular meshwork and uveoscleral outflow, tube shunts, trabeculectomies, and stents. To demonstrate the equation's capabilities, we can use it to describe tube shunt intraocular pressure mechanics. With the assumption that the encapsulated reservoir pressure, PV, is significantly below the intraocular pressure, we can use our water tank model, in which the flow out is dependent upon the diameter and length of the tube, as well as the fluid properties. At steady state, fluid in equals fluid out, and the time-related terms drop out. The encapsulated reservoir pressure, PV, is constant. Tube resistance to flow is a well-studied function of the change in pressure across the tube, intraocular pressure minus reservoir pressure. Taking the derivatives of both sides of the equation gives us the denominator term DFO dPIOP, which when plugged back into our original equation gives us a solution. Now, what does this solution tell us about tube shunts that the classic Goldmann could not? It tells us that it's modulated by the reservoir pressure. It also tells us that it's affected by the length of the tube and the viscosity of the fluid. And we know this intuitively by cellular debris and fibrin in the anterior chamber greatly increasing the intraocular pressure. Most importantly, it tells us that the diameter of the tube is the primary factor at a power of 4. So any variation in the manufacture of these tubes and that internal diameter would make a huge difference in the intraocular pressure. I hope with this justification we can retire the classic Goldmann equation with something which is descriptive of IOP mechanics. Thank you.